In this lesson, we are going to master the remainder and factor theorems. These theorems are essential tools in your additional mathematics toolkit. They allow you to bypass long division when finding remainders and provide a systematic way to solve high-degree equations, which is a common requirement in Cambridge IGCSE exams. Today, we will master the remainder and factor theorems, essential tools for handling higher-degree polynomials in your exams. The remainder theorem provides a shortcut to find what is left over after dividing a polynomial by a linear expression. Formally, it states that if a polynomial p of x is divided by a linear factor ax minus b, the remainder r is found by evaluating the polynomial at the value that makes the divisor 0. In the simplest case, if you divide by x minus c, the remainder is simply p of c. If there is a coefficient in front of x, like in a x minus b, we evaluate the polynomial at b divided by a. This works because we are essentially substituting the root of the linear divisor into the polynomial. Let's apply the theorem. Since we are dividing by x minus 3, our value for c is 3. Instead of performing long division, we simply substitute 3 into every instance of x in the polynomial. R equals p of 3, which equals 2 times 3 cubed minus 5 times 3 squared plus 3 minus 7. Let's evaluate this step by step. 3 cubed is 27 and 3 squared is 9. 2 times 27 gives us 54, and 5 times 9 is 45. Subtracting and adding these values, we get a final result of 5. Therefore, the remainder is 5. This method is much faster and less prone to calculation errors than long division. Today, we are looking at the factor theorem. The factor theorem is a specific, powerful application of the remainder theorem. It identifies when a linear expression is a perfect factor of a polynomial. The core condition is that x minus c is a factor of p of x if and only if p of c is equal to 0. If you substitute the value c into the polynomial and the result is exactly 0, it means there is no remainder. Therefore, x minus c must be a factor. In terms of application, this is essential for solving cubic equations and factorizing higher-degree expressions. In your exam, you will use this to break down complex cubic or quartic expressions into simpler linear and quadratic parts. If p of c equals 0, then c is a root of the equation, and x minus c is a factor. To show that x plus 2 is a factor, we must prove that the remainder is 0 when x equals negative 2. Let's calculate this. Negative 2 cubed is negative 8. Negative 2 squared is positive 4. The terms cancel out to give 0. Since p of negative 2 is 0, we have confirmed that x plus 2 is indeed a factor. By dividing the polynomial by x plus 2, we are left with the quadratic x squared minus 4. Notice that x squared minus 4 is a difference of 2 squares, which factorizes into x minus 2 and x plus 2. So, the polynomial has a repeated factor. Understanding the link between the factor theorem and the graph of a function is vital for A-star students. When we factorize p of x as x plus 2 squared multiplied by x minus 2, we can predict the graph's shape. Because x plus 2 is a repeated factor, the graph does not cross the x-axis at x equals negative 2. Instead, it is tangent to the axis, meaning it just touches it. We call this a repeated root. In contrast, x minus 2 is a single factor. This means the graph crosses the x-axis at x equals 2, which is a single root. The y-intercept is found by calculating p of 0, which gives us negative 8. Visualizing these points helps you verify your algebraic work during the exam. Let's look at how to solve for unknown coefficients. A common exam scenario involves polynomials with unknown constants, usually labeled a and b. To find two unknowns, the examiners will provide two pieces of information, such as one factor and one remainder, or two different remainders. Step 1 is to apply the remainder or factor theorem to each piece of information to create two algebraic equations. Step 2. Because these equations share the same variables, a and b, we solve them as a system of simultaneous equations using either substitution or elimination. This is a high-yield skill for Paper 1 and Paper 2. Let's solve for a and b using the two conditions provided. Since x minus 3 is a factor, the remainder must be 0. Simplifying gives 27 plus 9a plus 3b minus 12 equals 0, which rearranges to 9a plus 3b equals negative 15. Dividing the entire equation by 3 to simplify, 3a plus b equals negative 5. We will call this equation 1. Using the remainder theorem for the second condition, p of 1 equals negative 10. This simplifies to 1 plus a plus b minus 12 equals negative 10, then a plus b minus 11 equals negative 10, leaving us with a plus b equals 1 as equation 2. We can subtract equation 2 from equation 1 to eliminate b. 3a plus b minus a plus b equals negative 5 minus 1. This gives 2a equals negative 6, so a equals negative 3. Substitute a equals negative 3 into equation 2. Negative 3 plus b equals 1, so b equals 4. The values are a equals negative 3 and b equals 4. Always check your work by substituting these back into the first equation. Let's look at a typical Cambridge exam question. The polynomial p of x equals 2x cubed plus ax squared plus bx plus 6 has a factor x minus 1. When p of x is divided by x plus 2, the remainder is 12. Find the values of a and b, and then factorize p of x completely. Let's apply our strategy. First, we use the factor x minus 1. According to the factor theorem, p of 1 must equal 0. Simplifying this, we get 2 plus a plus b plus 6 equals 0, which simplifies to a plus b equals negative 8. This is our first equation. Next, we use the remainder information. When divided by x plus 2, the remainder is 12. So p of negative 2 must equal 12. Expanding the terms, we have negative 16 plus 4a minus 2b plus 6 equals 12. This leads us to 4a minus 2b equals 22. Dividing by 2 to simplify, we get 2a minus b equals 11. This is our second equation. Now, solve the system. Adding equation 1 and equation 2 eliminates b, giving us 3a equals 3. So a must be 1. Substitute a equals 1 back into equation 1. 1 plus b equals negative 8, which means b equals negative 9. Finally, factorize the polynomial. Substituting our values for a and b, p of x is 2x cubed plus x squared minus 9x plus 6. Since x minus 1 is a factor, we can divide to find the quadratic factor. Dividing the polynomial gives the quadratic 2x squared plus 3x minus 6. This quadratic does not factorize easily with integers, so we leave the final expression in this form. The most frequent mistake is using the wrong sign when substituting. If the divisor is x minus 3, you must evaluate p of positive 3. If the divisor is x plus 2, you must evaluate p of negative 2. Always think, what value of x makes the bracket 0? When using the remainder theorem, students often set the expression to 0 by habit. Remember, for the factor theorem, it equals 0, but for the remainder theorem, it must equal the given remainder value. Be extremely careful when cubing negative numbers. For example, negative 2 cubed is negative 8, not positive 8. Use brackets on your calculator to avoid these simple errors that can ruin your simultaneous equations. In exams, if you are asked to factorize completely, finding one linear factor is not enough. You must perform division to find the quadratic quotient and then check if that quadratic can be factorized further. In Cambridge exams, the word hence is a massive hint. If a question asks you to show a factor and then says hence factorize, you must use that factor to divide the polynomial. Do not start from scratch. While algebraic long division is reliable, Synthetic division is much faster for linear divisors of the form x minus c. Mastering this can save you precious minutes in paper 1. When solving for unknowns a and b, quickly substitute your final answers back into both of your original equations. If they don't work, you've likely made a sign error in your simultaneous equation steps. Don't just write down the simplified equation. Examiners give method marks for showing the initial substitution, like p of 2 equals 2 cubed plus a times 2 squared. Even if your final answer is wrong, you can still secure most of the marks. It is time to test your understanding. Please pause the video and attempt these 3 questions before we go through the solutions. Take your time with these, use the factor and remainder theorems exactly as we practiced. For the easy question, we need to find the remainder when p of x equals x cubed minus 4x plus 5 is divided by x minus 2. For this question, we substitute x equals 2 into the polynomial. Calculating this gives 8 minus 8 plus 5. So the remainder is 5. Now for the medium question. Given that x plus 1 is a factor of p of x equals 2x cubed plus 3x squared plus kx minus 6, find k. Since x plus 1 is a factor, p of negative 1 must equal 0. Simplifying, we get negative 2 plus 3 minus k minus 6 equals 0. This simplifies further to negative 5 minus k equals 0, which implies k equals negative 5. Finally, the hard question involves a polynomial with 2 unknown coefficients, a and b. The first condition is p of 2 equals 12. Substituting 2 gives us the equation 2a plus b equals 1. The second condition is p of 1 equals 6. Substituting 1 gives us the equation a plus b equals 3. Subtracting equation 2 from equation 1, we find that a equals negative 2. Finally, substituting a equals negative 2 into equation 2 gives b equals 5. Let's summarize the key takeaways from today's lesson. First, the remainder theorem allows you to calculate what is left over from a division simply by substituting a value into the polynomial. Second, the factor theorem is a specific case where the remainder is 0, telling us that a linear expression is a factor. Third, when you have unknown coefficients like a and b, you create and solve a system of simultaneous equations using these theorems. Fourth, remember the graphical link. A single factor crosses the axis, while a repeated factor results in a tangent point. Finally, maintain high accuracy with your mental and calculator arithmetic, especially when dealing with negative substitutions.